Okay, we'll start. Good morning, everyone. Start in a minute or so. Start sharing the screen. Okay, good morning. I hope all of you can see the screen. And as I had remarked towards the end of last class, we will today start with martingales. We will consider only discrete time martingales. So this x sub n, ym, y sub m, and all things will denote real valued random variables on some probability space omega fp. Stochastic process means a countable collection xn of real valued random variables where n varies over this. So that is because n is the time parameter. So discrete time martingales. Okay. What happened? Okay. So straight away we go to the definition. Let xn and yn be stochastic process. So in this process, the two processes sort of play slightly different roles. The yn process will be considered as something which is known to us. That collection is sort of known. And xn is how best one can predict certain things in terms of the known process yn. Okay. So we say, hello, can you hear? Did someone say something? There is some noise in the background, but that is beyond my control. It's happening in some other flat. Okay, we say xn is a martingale with respect to yn. If first of all, the xn, each xn is integrable. So the expectation exists. And this is the defining condition. So recall whatever we had done concerning conditional expectations. Conditional expectation as a random variable. So please refer back to your notes. That I think it is Markov chain 3 perhaps. So if the conditional expectation of xn plus 1 given y0, y1 up to yn. So we had remarked that conditional expectation of one random variable given a collection of random variables. That is, this is y0, yn up to y1 up to yn can be considered as a random variable on the n plus 1 dimensional space. So given this, we know from our what we had done earlier that this is a random variable which will be a function of the yi's, y0 up to yn only. And if that function happens to, that thing happens to be xn, we call this collection xn to be a martingale with respect to yn. So please note it down. So this is something like the given the y0 up to yn, how best you can have some prediction about xn plus 1. That is, it is a best predictor and all we will not prove, but just certain things are of course inherent in the definitions. So that is xn. So because of this x sub n will be a function of y0, y1 up to yn. note it down if you want.
And so expectation of all xi are the same.
Pardon?
Expectation of all xi are the same.
We'll soon see. Yeah, who is that? Kapil?
Yes.
Okay, good. Good guess. I mean, given the properties of conditional expectation, that's pretty obvious. Okay, note it down. So in this situation, this thing can be considered as the part of history up to time n, or that is the information available up to the time point n. So that is the, so in case, of course, yi equal to xi itself, then merely that x0 up to xn is the information up to time n. Okay. Of course, even each of these yi's need not even be real value. They can even be vector value. Each yi can be even vector value. And we make some kind of a small to reduce the terminology or our this thing to write or type. Whenever xi is the same as yi as it is here, or in some particular context, this yn is not important, or if it is very obvious from in certain context, we will omit any reference to it. In that case, we'll just say that xn is a martingale. So which means that what exactly yn is either irrelevant or it is known. I mean, that is a kind of the general this thing which is played. No, you make one definition and the definition is a bit too long to this thing. You always try to abuse by shortening it into something else. Okay, so we now, oh, see, sorry, if you have not noted it down, please. So we now look at certain elementary facts. Oh, there's an L missing here, elementary. Look at some elementary facts concerning martingales using properties of conditional expectation. I am not listing them as proposition and things like that. Just so. So by the second condition, that is basically the defining condition of a martingale. Yeah, this one. We have this, I have just written that equation, in the interchanging the left side and the right side. So from this, since from the knowledge of the values of these yi's determines the value of x. So if you say that y0 equal to I0, y1 equal to I1, yn equal to in, and things like that, from that you will know xn can be expressed as a function of that I0, I1, etc. So the values of the y0 to yn determines the value of xn. You may need all these values or even some of them might be enough, but nothing more than this. That's the idea. So xn can be considered as a function of y0, y1 to yn. So that's what it is mentioned here. Note it down if you want to. So recall one of the properties of conditional expectation we had seen. For any function g, of course, that is a condition here. The g of this thing should be integrable. In that case, the conditional expectation of this g of y0, y1 to yn, given these things, is that function itself. Because it's already a function of these things, so it is itself. Remember that this conditional expectation is a random variable. So therefore, of course, conditional expectation of xn given y0, y1 to yn is xn itself, because the earlier thing from this we know that xn is a function of these things. So it is basically just a tautological statement. Okay. So xn has, of course, we assume that every xi has finite expectation. So since xn plus 1 has finite expectation, look at that equation which we have denoted by this spade suit in Markov chains 3, and that basically says that gives this equality. And using that only, Kapil immediately guessed that it should be this. And therefore, just keep on doing this. Then you see that expectation of each xn is same thing as expectation of x0. That is, the mean value or expectation doesn't change. Not it down. Okay. So let us look at some examples. The first example, which is side of the most obvious, sums of independent random variables. So let y0 be 0 and let y1, y2, etc. be independent random variables. We are not saying that all of they have the same distribution. They are not necessarily IID random variables, just independent. And all of them, all the yi's have finite expectation. And not only that, the expectation of each yn is 0. So now you define x0 equal to 0 and xn equal to y1 plus y2 plus yn. Of course, you can even include y0 also here. Doesn't matter, but this is simpler way of doing it, writing it. So this is a sum of n independent random variables, yi. And it is a fairly simple thing to verify that this xn is a martingale with respect to y. So to do that, you use one property of conditional expectation, which we had given earlier because of independence. Because of independence, the conditional expectation of something given the others turns out to be the expectation itself, the unconditional expectation. Not into. Yeah. So in particular, if these things are IID random variables, then these partial sums of these IID random variables with zero expectation form a martingale. Of course, if these things don't have expectation 0 for all of them, from each you subtract that and then add. So that kind of an object will be a martingale. So sums of independent random variables, can be considered as a Markov chain, as be considered as a martingale, and things like that. So study of sums of independent random variables has formed a kind of a backbone to this in this thing of probability theory and statistics. Of course, driven by applications. And you also know that independence is a fairly strong assumption. Okay. Next example. This is variance of a sum. So suppose expectation of each yk is 0. And each yk is also square integrable. Of course, these are assumed to be IID random variables. So all the moments, whenever they exist, will be the same. So expectation of yk squared is, let us say, sigma squared for all k. Okay. So define x0 equal to 0 and xn to be summation k going from 1 to n yk, the summation whole sum squared minus n sigma squared. So this is the this sum is the partial sum, k going from 1 to n. And this is the sum of, not sum of squares, then you take this variance. So this is the kind of variance of the sum. For this random variable, summation yk, k going from 1 to n. For that random variable, you will have mean 0 because of this. So one considers the variance of that. So that itself forms a martingale. So to verify that this is a martingale, first of all, one has to see that the expectation of each of this guy exists. Of course, that follows from our assumption that each yi is square integrable. So this is an exercise for you to show that, of course, this kind of exercise you would have done your earlier course in probability. So expectation of mod xn is dominated by 2n times sigma squared. All this kind of verification is also a good exercise to sort of review or refresh your knowledge about basic probability. Note it down if you want. Okay. So conditional expectation of xn plus 1 given y0, y1 up to yn. So xn plus 1 by definition is the sum up to n plus 1 of the y case, but that yn I have separated out and the other things I have written together. And this sum together, the square is taken, minus n plus 1 times sigma square. So the next step is just has expanded out this square of this sum. And this is of course that. And these guys would sort of get cut in the process. You should imagine that it goes all the way up to yn. It is not as bad as some of the earlier stages where there was some kind of a censoring was applied by the beamer. So now this summation k going from 1 to n yk square minus n times sigma squared. In this n plus 1, n times sigma squared, that is your xn. And we know that xn is a function of y1, y2 up to yn, because remember that the xn is defined in terms of this. So we already know it is a function of that. So that comes out of the conditional expectation. So that is what we have written here. And what remains is n plus 1 squared plus this. So that since conditional expectation is a linear operation, we have split that like that. And even here, this sum is a function of that. So, and that is taken out of this conditional expectation. So here, basically 2 steps are involved. So when we are taking conditional expectation of this given these guys, so that sort of comes out. And also here there is a minus sigma squared. That also I think is at the end. Minus sigma squared is there. So now yi's are independent. Therefore, conditional expectation yn plus 1 squared given this is just expectation of yn plus 1 squared, which is equal to that sigma squared. So those 2 guys cancel each other. And now here, look here. So this is the conditional expectation of yn plus 1 given y0 up to yn. And these are all, yi's are all independent. Therefore, this conditional expectation is the expectation of yn plus 1 itself. But expectation of all yn is 0. So that this vanishes. So there is a minus sigma squared still in balance, which is not reflected in this, that has got cut off. And that cancels with this guy and so on. So please supply appropriate reason for each step. So it's an exercise one. Orally it has been mentioned. Note it down. So if you are writing it down here, just please be careful here. So this, apart from this thing, there is one term which is minus sigma squared, which is coming from here. N times sigma squared have been accounted for here. So that minus sigma squared is there. And that minus sigma squared will get cancelled with this, because this is going to be because of the independence of yi. This is just expectation of yn plus 1 squared. So that is sigma squared, we know. So that cancels. And here, because of again independence, the conditional expectation yn plus 1 given this is expectation of yn plus 1, which is 0. So in this computation, you have used certain properties of conditional expectation we had seen earlier. Note it down carefully, please. Okay. So next example, this is basically coming from Markov chains, called induced by martingale induced by what may be called right regular sequences for Markov chains. let y0, y1, y2 be a Markov chain with state space S and transition probability matrix P, which is Pij. Okay. So we say F is a bounded right regular sequence for P. If that is, F is, of course, F is a function on the state space. That, yes. So it is a bounded function, non-negative function, and it satisfies. For example, you already know one example of such an Fi, that is f of I equal to 1 for all I. And since P is a stochastic matrix, that will give you 1 equal to summation Pij, summation over j.
Basically, an eigenvector of eigenvalue 1.
Yes, right eigenvector. Right? It's a right eigenvector. Unfortunately, the connection between eigenvalues and these things, I didn't have time for that, because that would have involved proving a long theorem called Perron-Frobenius theorem. I thought I will assume that and proceed, but that would not have been very satisfactory. So that would have, for example, given you some information about the rate of convergence in the case of finite state spaces. And there, under certain circumstances, it will turn out to be the one would turn out to be the biggest eigenvalue, and the others, and among the others, some eigenvalue. But instead, I proved the other one, that which also gives you the rate of convergence, for which we have proved almost everything. So I adopted that. Yeah, as Kapil has pointed out, this F is a right eigenvector corresponding to the eigenvalue 1. Okay. So given this function, that rather this is sequence because S is a countable state space. Of course, if it is a finite state space, this will be a finite sequence. There will only be F1, F2 up to some Fk. And set Xn equal to F evaluated at Yn, where this Y is the Markov chain. Since F is assumed to be bounded, it is clear that expectation of Xn is finite for all n. Note it down, please. Okay. So to prove the Markov property, so now we are going to adopt. See, earlier we could easily argue that you take this conditional expectation. I mean, we are treating conditional expectation as a random variable. We could easily, from the properties of the conditional expectation, which we had seen as a random variable, we could deduce this. Now we will adopt different strategy. So we will argue that the thing given y0 equal to I0, y1 equal to I1, etc. This, then you take the conditional expectation. So in this case, this will be a number. And for doing that, we are going to use the Markov property. So here this involves an exercise. One way you can do is that you write, of course, the way you have to do is write this as, since by definition of this you have to take this summation over the appropriate sample space of the value of fyn plus 1 at that point, and then conditional probability of yn plus 1 given this. And when you take the conditional probability of yn plus 1 equal to some j given this, in that you apply the Markov property. So all these I0 to in plus 1, that guys will disappear. Only the last one will remain. And then again, go back in terms of conditional expectation. Or even from that step itself, you can get this, because this will be f of, let's say, yn plus 1 equal to j, so that let's say fj times this, that probability of yn plus 1 equal to j given yn equal to I is this pij. Yeah. So in this case, you don't come write that at that point. You write it as summation over j fj and then that probability. Write it down clearly. And in the last step, you use this equation. Here you are using this equation. So this is nothing but this I, this is f of yn equal to I, f at yn equal to I. So we have expressed this thing evaluated at every I0 or this thing as f evaluated at yn equal to 1, yn equal to I, sorry. So therefore, this is a function, and that function is precisely fxn, or rather fyn, but by definition it is this. Fyn is our xn. Please note it down carefully. So this is the last slide for the day. So if you want me to go back to any of the previous slides, I can do that. Otherwise, we can stop sharing and end the session for the day.
Is today's class over?
Yeah, today's class is over. Yes. I was waiting for you to say that. conscience keeper. Okay. So let us stop sharing and take care, all of you. We will see you on Wednesday.